Hi everyone, I'm Pei. I'm a PhD student from UTS and the visitor student from UNSW. I'm excited to talk you about the Iterative-Epoch online cycle animation for context-free language reachability. This work is co-authored by the Yuxiang and advised by the Professor Sui and Professor Xue. Let's start beginning from the overview. This paper improved the scalability of context-free language reachability by reducing the graph size for online cycle elimination using an Iterative-Epoch framework. So let's start from a little background. What is context-free language? It is a series of strings generated by the context-free grammar. Specifically, an instance of CFG consists of the following components. Firstly is sigma, which stands for the alphabet containing all the symbols used in the CFL. N is a set of non-terminal symbols. T is a set of terminal symbols. P is a set of production rules. And also very important is a start symbol, S. Where is the language starting to generating? So starting from S, all the terminal strings are belong to the CFL can generated by one or more production from the CFG. For example, consider the context-free grammar with start symbol S. The terminal symbol T of set A and B, the productions S equals to A, S, B, and epsilon. The epsilon here denotes an empty string. According to productions, S equals to A, S, B, the starting symbols can generate it, again, A, S, and B. Then by applying the S equal to epsilon to A, S, B, we got a string AB, which belongs to CFL generated by the grammar. Besides, we can also apply S equals to ASB again to ASB to generate AASB, which can then produce a string belongs to the same CFL. In fact, any string in this form where n is a non-negative integer belongs to the CFL. In program analysis, a large variety of programs can be formulated in the CFL reachability, including the points to analysis, data flow analysis, shape analysis, polymorphic flow analysis, and tent analysis. In general, given a context-free language grammar, and age-labeled graph, a CFL reachability instance reach is to determine whether particular load pairs are connected by a path whose age labels sequentially from strings accepted by the CFG. Specifically, for all the ages vi, x, vj in G, initially, the G contains only ages labeled with the terminals. Solving CFG follows a dynamic programming scheme called summarization, which is a reverse process of string generations. Given a path, the path is denoted by P from V0, V1 to Vi, with label is associated Y. If there exists a productions along the X from Y1 to Yn of the production rules, whose right-hand side is exactly the sequence of ages labels of P, then P can be summarized to an age. If there's no already in the graph, then you will be added to the graph, make the X relationship to be explicit. Formally, 2 nodes is said to be X reachability from the Vj if it can be summarized by a path from Vi to Vj. Given these specific sources and the sink, CFL reachability is to determine all each pairs, whether it is S reachability from Vj. So, how to exactly to solving these issues? It's usually solving by a standard dynamic algorithm, which will be in detail in the papers. This algorithm requires an input grammar to be normalized. The right-hand side of each production has both 2 symbols. For example, production as A as B needs to be converted into A equals to AS and S equals to capital A and B. This algorithm maintains a work list W to record all ages. whenever an edges is added to the graph, it is also added to the work list. It starts beginning from the procedure init. What it does is it moving all the edges from edge set to the work list. Then followed by it, if we have any epsilon rules, it will add associated generate edges to the edge set and the work list. Then starting to the dynamic solving process, it will pop each edges from the work list and check all the rules. If these rules can be generate new edges, then you are moving to the work list and moving to the edges. Then the same process applies to the two terminal on the right-hand side process. Then you will check its predecessors, and then if it can be generated a new edges, you will move the new edges to the edge sets and the work list. And then you will does the same process to its successors and doing the same process. So the problem of this process is every time we checking the rules, it generates a lot of computation redundancy because of the cycles. So our aim is to online cycle elimination of this process. So here we give a motivation example. So on the right hand side we have a CFG. The main gist here is we have a symbol which can be generated and transitive along this graph. If we're solving this graph on the right hand side, then we are generated a much complicated soft graph, G prime. We can see that in the middle of this graph, they have a lot of S edges being transferred along these two cycles. So instead of doing this, we can have a new 3-step online cycle elimination solving. In the first step, we start just solving the transitive symbols. And then we consider the generating rules that can generate in the A symbols, which can be seen on the right-hand side. Then after that, we collapse the cycle occur in this process. And then after the cycle elimination, the graph has been shrunk. So we then consider other A-generating productions. So comparison with standard solvings, the online cycle elimination, after that, the graph is being shrink, and so on, the computation cost is being reduced. Given these motivations, we can formally define our Iterative-Epoch algorithms. So the main difference here is we have two work lists. The work list first is a work list holds the unprocessed edges from A generating step. And another work list, no A generating work list, holding all the unprocessed edges from no A generating steps. So in the initial step, you also carry all the epsilon edges to the edges and work list. Then the second step, which is the essential part, we will only consider A-generating productions, and you will compare all the first symbol and the double production scenarios. And then these edges will only move to the work list, W. And then is the collapse cycle steps. This step we use SCC to collapse all the cycles. And then we consider all no A-generating steps, which will move all the generated edges to work list no A-generating. Iterative-Epoch algorithm is not limited to the standard solving, but also have same strategy can be implemented on other improved algorithms. For example, the POCR can be implemented together to have iterative-epoch partial order CFL-reachability algorithms. Aegis derivation can benefit from both cycle eliminations and the spanner tree-based partial order derivations. So we have two kinds to have the evaluations. First one is value flow analysis, and second one is fail-sensitive analysis. For the benchmark for value flow analysis, we're using the SPEC 2017 benchmark. And for the fail-sensitive analysis, we use the CAPO benchmark sheet. So let's first check how much it actually being reduced of nodes and edges. For value flow analysis, the average node has been deducted 10%. And for alias analysis, the average node deduction is around 5%. However, the average edge, due to those limited number of nodes, are significant. We can see that the value flow analysis, we reduce around 50% edges, and similar applies to area analysis. In terms of how many epoch and collapse time has been as an overhead, so they are average only 9.7 epochs to eliminate all the possible cycles during the solving, and also 6.4 for the area analysis. As a result, the speed up of value flow analysis on average it was 17 times, and for alias analysis it was pretty much similar with 13% speed up. And for the reductions is for the status of reductions of redundancy, you can show that the IEA has around 50% of value flow analysis, and area analysis has 45% reduction. In conclusion, this talk is to increase the CFL-reachability for various clients as long as the grammar has been approved to use the IEA. Thank you, everyone.
Okay, questions? The session is not merely a discussion between the session chair and the presenter. It's supposed to be an opportunity for everybody to participate. So I was curious sort of how this fits into your broader research agenda, like sort of what's the long-term vision or what's the context in which you're doing this work?
So basically why we're starting to do this work is because we are trying to analyze using CFL-reachability in some larger amount of code, but what facing is actually limited to the scalability. So this is one point. We possibly extend this work to parallelized analysis, because for this work we does not consider the parallelized way. So I think this is a future work, and possibly we might extend the works to other clients outside the realm of just analysis and value flow analysis. Yeah.
Yeah, go ahead, please.
So thanks for the talk. I was wondering, you talk about how a lot of problems can be modeled as CFL reachability, and I saw another talk yesterday on CFL-OBDDs. So my sort of understanding from all of that is that I guess CFLs are an effective way of modeling things across a lot of domains. My question for you is, why do you think that is, and what do you think is there anything you can say about what structure you think CFLs capture?
I understand your backgrounds, but for the very last questions, I didn't get it. Would you mind repeat that?
Oh, why do you think CFLs are such an effective way of modeling so many different problems?
I think CFL-reachability is very basic and fundamentals. So because it's just a graph way of representation of a graph program, which is actually all the graph program you can model to a graph. So I think it's very universal, and it can be transferred to other type of problem definition. We can transfer to RSM, so you can integrate different programs using different problem definition, which is great. Yeah.
Thanks.
Thank you.
I'm curious, do you feel like you've reached a canonical CFL, or are there other collapsings, like collapsing chains or trees or whatever? Do you think there might be other sources of optimization besides the one you just did?
Sorry, would you mind repeating the questions? I think the volume is a bit low for me.
Okay, so you just did cycle elimination.
Yes, cycle elimination.
Check.
Yeah, check.
That worked.
Yeah.
Are there other things you could do? So if you look at the output of these grammars, you could see, like, are they still noisy, extra junk in them? So you think, are there more optimizations that could be applied that you haven't thought of? Or do you feel like you're close to the canonical, minimal CFG? I mean, there's a notion, there's like with Kolmogorov complexity, there's the minimal grammar. It exists.
Yeah.
So the question is, how close are you to that grammar now?
I think these words are more applied for strength input graph. So I think there are other work to, like, using RSM to reduce the grammar. I think our work are not considered a kind of orthogonal to this type of grammar optimizations. Yeah, we are just more like check this grammar whether it is have the transitive symbol here. If we have, we can use this type of optimizations. Yeah. Thank you.
Okay, let's have one more round of applause for our speaker.